Hi, I'm Jacqueline Edge, and I work at Imperial College London. I'm the project leader for the Faraday Institution MultiScale Modelling project on lithium-ion batteries. I'm here to guide you through what this project is about, who is involved, and our main achievements so far. The project is divided into three work packages. Work package 1 is looking into parameterization of models using both experimental and digital techniques. Work package 2 is extending the physics and degradation mechanisms incorporated into our whole cell level models. And work package 3 is developing algorithms to operate battery packs. We can build digital models or simulations to predict the behavior of real devices under different conditions. Cheaper and faster than building real-world prototypes, simulations can be altered and rerun to test different designs. But to trust their predictions, models should be as accurate as possible. Electric vehicles get their energy and power from battery packs, collections of cells working together. Each cell is a highly complex device consisting of different layers, and their behavior depends largely on their structure and materials. So before we can safely make any improvements, we must first understand the physics and chemistry involved. We can study the dynamic behavior of atoms within the materials. If we zoom out, we can simulate a whole cell. Zooming out further still, we can model the whole pack to devise the best way to operate it safely. This helps us see how it will operate under different conditions, enabling us to model the whole battery pack. Each simulation scale builds on the insights from the lower scale models, ultimately leading to improved accuracy. Professor Greg Offer at Imperial College is the principal investigator of the project. Greg, what motivated you to start and lead this project?
I'm motivated by a desire to solve some of the biggest challenges facing our society. Success for the MultiScale Modelling project involves putting together the latest understanding of lithium-ion battery degradation into a common modelling framework that can be reliably and affordably parameterized both experimentally and virtually. It is important that our models can be trusted and used by industry to solve real-world problems. This means the codes have to meet professional standards and the results must be validated. Ultimately, we believe that the results of our project have the potential to deliver a step change in the ability to predict the performance and lifetime of lithium-ion batteries for multiple applications. Our focus in years 4 and 5 has shifted towards including multiple models of degradation into our common modelling framework, alongside the continuing challenges of parameterization, both computational and experimental, validation, computational efficiency, and using the models within applications. The goal is to provide industry with tools capable of predicting lifetime or that can be used for diagnosing state of health during operation. We have also expanded our work in collaborations on life cycle analysis and technoeconomics. Indeed, these show that the biggest uncertainty, which has the largest effect on life cycle cost and emissions, is lifetime, justifying our focus on developing tools for industry to enable them to optimize the whole life cycle of a battery.
Improved accuracy starts from atomistic models, simulating phenomena that we can't observe directly, the interactions between atoms. With simulations, we can predict the properties of compound materials. However, each additional atom greatly increases the number of calculations per second. We want to simulate the interfaces between battery materials because this is where all the important chemical reactions happen. But this requires tracking tens of thousands of atoms. One tip is a new tool which uses clever mathematical tricks to reduce the number of calculations needed per atom, making interface science possible. The project's atomistic modelling work is led by Professor Chris Skylaris, a co-investigator of the project.
Hello, my name is Chris Skylaris, and I am a professor of computational chemistry at the University of Southampton. My research is on developing methods for first principles quantum mechanical calculations. These methods traditionally have a computational effort which increases with the third power, increases very steeply with the number of atoms, and they are limited to small simulations of a few hundred atoms at most. In batteries, we are interested in much larger domains which consist of many thousands of atoms. So we have reformulated the quantum mechanical theory, the density functional theory as it is called, the one we're using, in such a way that we can do simulations with tens of thousands of atoms. This linear scaling reformulation of density functional theory is called one-step. We have been developing also on top of these quantum mechanical methods models to describe the environment of the battery, so the solvent, the electrolyte, and the voltage. And as you can see, currently we are working on the atomistic description of the electrolyte and the processes that happen there, the speciation, the degradation, and ultimately this tool will allow us to understand also processes such as the solid electrolyte interface formation in batteries.
The next scale up is a continuum model of a whole cell. At this scale, we can no longer track individual atoms, so material properties need to be averaged. For example, to model diffusion, we use an effective diffusion coefficient through an average lump of material. Similarly, electrochemical reactions at an interface are described by an equation approximating a lot of physics into something that can be solved more quickly and easily. As long as the rate-limiting process is being correctly identified, we can disregard the other processes to reach an accurate approximation. And now we go to Dr. Robert Timms at Oxford, who will tell us more about PyBAM, one of our cell-level design tools.
Hi, I'm Robert Timms from the University of Oxford, and I've been working with the Faraday Institution since 2018 as a postdoc. And as part of my work, I've been working on the open source battery modelling package, PyBAM. PyBAM stands for Python Battery Mathematical Modelling. So part of PyBAM's mission is to accelerate battery modelling research by providing this open source framework. And the goal of that really is to enable multi-institutional interdisciplinary collaboration. Around PyBAM, we're trying to grow a very active battery modelling community. And as part of that, people can get involved in a number of different ways. So since the project has started, we've now got almost 40 contributors, and half of those are not affiliated with the Faraday Institution. And I think that really goes to show the success of the project that we're now starting to draw in contributions from people outside of our circle.
To tell us more about using PyBAM, we go to Dr. Tom Tranter at UCL.
Hi, I'm Tom Tranter. I'm a postdoc at UCL, and I've been part of the MultiScale Modelling project for a couple of years. And I'm working on battery problems at larger scales. So the first project that I worked on was building a model of a cylindrical cell from a CT image. We analyze the image and extract the current collectors and make them into a resistor network. And the nodes of the resistor network are connected together with electrochemical simulations. These are calculated in PyBAM. Using the framework, we applied the model to the larger 4680 format Tesla cell, and we investigated thermal issues that may occur with different numbers of tabs. Using a standard 2-tab configuration, the ohmic losses around the jelly roll are very high due to the long length of the large spiral. When you use the newly proposed infinite tabs that Tesla have patented, the ohmic losses are much less, and that results in less heat being produced and a much lower cell temperature. We built a rig of 32 cells connected in a 16 in parallel 2 in series fashion, and we monitored cell temperature, voltage, and current during different duty cycles and constant current, constant voltage profiles. We modeled the system as well, and the system was air-cooled at different rates, and we were able to observe differences in the temperature of the cells due to the different cooling effects in the configuration of the pack, and the model was able to capture these effects.
Dandelion is another of our cell-level models built for speed. Dr. Ivan Korotkin at the University of Southampton will tell us more about it.
Hi, my name is Ivan Korotkin. I'm a research fellow at the University of Southampton and one of the developers of Dandelion, a high-performance cloud-based solution for battery simulation. Unlike other software, Dandelion demonstrates incredible scalability and speed, providing a high-resolution, physics-based, thermally coupled 3D model of entire battery. And in this example, you can see pouch cell battery simulation. The first working version of 1D Newman model can be tested online on dandelion.com as a service, no installation required. The scalability potential of the code allows us to tackle incredibly huge systems up to many thousands of different models, providing very detailed simulations. The full 3D models of pouch and cylindrical cells are planned to be released online as a premium service that can be used as a sound basis for battery cell design optimization, or literally as an electronic twin of a real battery.
Another important aspect of battery operation is thermal management. The cell cooling coefficient was established as a metric to compare how well cells have been designed to reject heat. Since publishing, members of the MSM team have worked with industry on a sprint project called TopBat to put what we learned into practice and explore the effect of improving the ability to reject heat on a cell's performance, usable energy, and also lifetime. The results have led to 2 Innovate UK projects, one with Amity Power and another with British Volt. Dr. Alistair Hales developed the cell cooling coefficient at Imperial.
Hello, I'm Alistair Hales, a lecturer at the University of Bristol and a former research associate from Imperial College London. The cell cooling coefficient is designed to break down barriers which prevent cell designers and battery pack engineers from effectively designing thermal management systems. With current thermal modelling processes, you would need to parameterize every row of this table, and that would take many hours or days. What's more, there are certain measures, such as electrode thermal conductivities, which are very difficult to extract accurately. With the cell cooling coefficient, we approach the problem differently. We generate heat from within the cell, and we measure the rate at which heat is removed from the cell. The CCC is independent of cell usage, therefore it is a constant for a given cell and a given thermal management method. Our most recent research has explored using the cell cooling coefficient as a design tool. In doing so, we highlight a link between better thermal management, better balancing, and the cell's electrochemical operation, and ultimately, lithium-ion cells' performance over its lifetime.
We now move to the next scale up, which is control modelling for battery packs. To operate batteries safely and effectively, we need algorithms that can monitor the battery's internal state and make decisions quickly. But some aspects of the internal state cannot be measured and must be estimated through simulations. Electrochemical models like the DFN model are too complex and slow. Mathematical techniques allow us to simplify the models but keep the accuracy so that they can be used alongside the battery and help the battery management system to make rapid decisions. Ferran Brossa-Preneur works at the University of Warwick on reduced order models for battery control.
Hi everyone, my name is Ferran Brossa-Planella and I'm a research fellow at the University of Warwick. I've been working on the MultiScale Modelling project for about 3 years now, and my work has focused on deriving reduced battery models. In this first example, we start with a coupled thermal DFN model, and we derive a reduced model based on 2 assumptions: small deviations from the open circuit potential and slow heat transfer with the environment. The reduced model, which we call TSPME, retains most of the accuracy of the full model while being much faster to solve. For degradation, we have started from the DFN model with the side reaction and porosity change, and applied the same reduction techniques. This is still work in progress, but the preliminary results show that this reduced model agrees very well with the full model while being much faster, opening the possibility to deploying it to real applications. We're also developing control algorithms to implement fast charging while avoiding degradation. And here is a very nice piece of work by my colleague Yashing Ren, which uses a single particle model to estimate the anode potential to prevent lithium plating. We can see in the plots that the new anode potential estimation algorithm provides faster charging times while keeping the anode potential above 0.
The accuracy of a model depends on its assumptions about the properties of the battery. These are defined by a set of input parameters about, for example, how easily lithium ions can move between the electrodes. This and other properties usually need to be measured in a laboratory environment and may require the battery to be taken apart. This can be a costly process requiring highly skilled researchers and expensive equipment. About Energy is a new company emerging from this project, aiming to reduce the time it takes to parameterize new battery models so that they can be tailored for specific battery types and applications. Kieran O'Regan is a founder of About Energy.
My name is Kieran, and today I'll be speaking about our spin-out company, which is formed from the University of Birmingham and Imperial College London, called About Energy. About Energy is offering a tailored battery parameterization and testing service to industry with the aim of helping them improve the accuracy of the models they use in research and development. One of the main obstacles to improving model accuracy is the quality of input data used, known as parameters. Between the University of Birmingham and Imperial, we have developed a suite of tests to improve the accuracy of the data we can extract from batteries. And this relates to the electrochemical, thermal, and aging properties of battery. We package this information into different types of models, equivalent circuit, physics-based, and thermal models to improve the accuracy of predictions we can make about battery behavior. About Energy is trying to decentralize battery testing, parameterization, and modeling by offering this service to industry. So if you're interested in working with us, please reach out to myself or one of my colleagues.
Finally, we come to the broadest modelling scale, that of modelling whole systems across their life cycle, which is my field of research. Batteries are used to power a range of everyday products, from mobile phones to medical devices, and now also electric vehicles and backup for power grids on a global scale. Life cycle assessment models are powerful tools for assessing system-wide impacts, both economic and environmental, and considering all stages in the battery value chain. Environmental impacts include water use and the release of greenhouse gas and chemicals. They can be used to predict impacts of future developments, such as new battery materials, designs, or management systems. At this scale, it is possible to identify system-wide trade-offs and solutions. Dr. Laura Lander and I worked together at Imperial College, looking into the techno-economics and sustainability of lithium-ion batteries.
Hi everybody, I'm Laura Lander. I'm a postdoctoral research associate at Imperial College London in the Electrochemical Science and Engineering group, and my research focus is on the sustainability assessment and techno-economics of lithium-ion batteries and next-generation batteries for EV and grid storage applications. In order to develop truly sustainable batteries, we have to be aware that future developments, be it new materials for lithium-ion batteries, new pack designs, or a whole new battery system, will have an impact on the overall sustainability and techno-economics of the battery system. To assess the impact of the battery use phase on cost and sustainability, we developed lifecycle cost and carbon footprint models which take into account the battery lifetime as a function of temperature. Sensitivity analysis showed that indeed the battery lifetime is a crucial factor in order to improve the lifecycle carbon footprint and cost. Implementing those lifecycle cost and carbon footprint models into a real-world application will ensure that new battery developments will lead to an optimized balance between performance, sustainability, and cost. In the first stage, we apply those models to emergency service vehicles, moving towards zero-emission fleets.
We are collaborating with Williams Advanced Engineering, where Dr. Hugh Möller designs battery packs for real-world automotive applications.
My name is Hugh Möller. I'm the principal engineer of Williams Advanced Engineering, where I lead the team of Advanced Battery Project, which is responsible for the development of cell-driven battery pack performance and safety on our electrification programs. SPICombat is a collaboration project between Imperial College London, London Fire Brigade, and Williams Advanced Engineering. It is a program where we are trying to electrify the next generation emergency response vehicles to accommodate their unique usage cases and requirements, such as vehicle propulsion, pumping, and fast charging abilities. This was a great opportunity for combining the skill sets and experiences from our 3 companies and institutions to not only derive a pack that can do the job at high performance, but also be sustainable at the same time. Due to the specialized application of this emergency response vehicles, there is a lot of opportunity to do something novel. And Faraday or Innovate UK funded project structure is very valuable for such collaborative project.
To conclude, Professor Harry Hoster will give us an overall perspective as co-investigator of this project.
In our consortia, we work across disciplines, which really gives us an exponentially higher output than we would be able to achieve in our own research groups. And this high density and bundle of expertise makes us go-to places for international collaborations. So we have developed those modeling tools that other people around the planet started to use. We can bring in those tools and our experience with them as expertise into new collaborations, which opens totally new doors for us. And at the bottom line, this is really very, very fruitful.
I hope that gives you deeper insights into the MultiScale Modelling project, and thank you for watching. Please visit our websites to find out more.